Hello, everyone. Can you see the screen? All right, very good. My sound's okay? Can you guys hear? Okay, perfect. All right, let me get started here. All right, so last lecture we talked about the some pretty basic concept and equations for buckling and fatigue. It turns out that the buckling resistance of plate has a lot to do with the D matrix in the plates. So if you look at the equation, there's a few analytical models. You can calculate the buckling load of a composite plate in a closed form solutions. So we looked at a few of those at a specific boundary conditions. So this is the simply supported cross ply a solution like this, and then and symmetric angle ply under shear, things like that. So what I want to point out that you can actually estimate buckling load based on your use your CLD calculator. I did a very simple calculation here. So basically, all you need to do is to input your layup as you did before, and then you extract information from the D matrix, like this matrix here, for this layup, and then you can play with if in sometime your job calls for some estimation buckling load of certain layups, and you can use the CLT code to calculate that. So I use an equation for cross-ply. This equation I programmed in. It takes the D matrix and then A and B are dimensions. M is the half wave number. Basically, it's the mode, buckling mode parameter. M equal to 1, 2, 3, 4, things like that. When M equal to 1 is a mode 1, 2 is mode 2, and things like that. So I did very simple calculation. Basically, it's a laminate under a uniaxial compression. What is buckling load? So I put these. I extracted a D parameter from the matrix here, by this matrix, and then I put dimension. These are inches. I put A and B, and then mode number. And this equation, once you program it in, it'll automatically calculate the buckling load. And then you can play with the layups. Let's say you're gonna go with everything 0 degree. You see the buckling load changes. Dimension wise, you change dimension, buckling load changes. You change the mode number. This is mode number 1, mode number 2, mode number 3, 4, and 5. The higher the mode number, the higher the buckling load. So usually the lowest buckling load is associated with the mode number 1 half wave. And then I can change the ply to, let's say, a cross ply with 90s. Let's say with 90s. I put 290 in. The buckling load updates and see a little higher now. And I can do 45, so on and so forth. So basically, I just want to point out that you can use this code for that, this calculation for that purposes. In case you need, you first find some solutions and then you program in and then use your CLT to calculate D matrix, this matrix right here. All right, any questions, comments? Okay, I want to basically run through an example with numbers on the thermal stress calculation. And then you can use this set of data to calibrate your code. How many of you have finished programming your thermal stress part? Have you? Let me see some response. if you have, how many have started working on thermal stress? You can raise your hand if you have started working on thermal stress part of it. Okay, Thomas started it. That's the remaining functionality I want you to finish on your CLT code. And then we can, once that's finished, we'll just start doing a last final project with the CLT, and that will be end this. That will be the end of this course. So make sure you start on that, and we'll work through the last mile for this course. All right, so I'm gonna basically quickly go over the equations that's involved in this calculation. You can stop me anytime you want to ask questions. It's very similar to the calculation you have already done. So quickly, here is the sequence of calculations. There are a few slides on derivation. So the most fundamental assumption is the total strain is the sum of mechanical plus thermal, or the mechanical strain is the total strain minus thermal, like this. This is the fundamental assumption made in the thermal stress calculation. Basically, the thermal strain is due to thermal expansion of the constituent materials, and then the parameter that governs thermal expansion is delta T. Delta T is the change of temperature from certain hypothetical stress-free temperature. You assume at a certain stage of manufacturing, let's say during curing, there is a state. The material is stress-free. And then the material gradually solidify the matrices, and then the differences are frozen in, and as such, you have thermal stress. So that term, alpha delta T, is the representing the material deformation due to change of temperature. Okay. All right. So if you glue a bunch of plies with different orientation, different thermal expansion together, what happens? They will have to strike a balance. None of them can do the things according to its will. Let's say layer one want to expand certain dimension in certain directions. Lamina number two want to do differently, and so on for 3, 4, 5, 6, whatever. Once you glue them together, they have to agree upon a common set of deformation everyone's happy with. So they fight within each other. They achieve a balance, and then that balance is not it's free thermal expansion. There are some differences. That differences is the thermal stress. It's a thermally induced mechanical stress. Okay. So basically, if you glue a bunch of layers together, they have different thermal expansion. So a mechanical stress strain is guaranteed due to the misfit. Okay, and this will be the misfit strain, and then you can calculate. Once you figure out the misfit strain, you can calculate the misfit stress, what we call thermal stress. They are related through the same matrices, basically. All right. If there is a thermal effect in combination with external loading, then the total mechanical stress will be the thermal contribution, thermal stress superimposed by the mechanical stress. In this example, we assume there's no mechanical loading, just the thermal effect. All right. And once you glue all the layer together, the layer come to self-equilibrium. There is a condition. So if cut up laminate in half, you add all the resultant force from every layers together, and you should have a total stress of 0. Okay, so that's the condition. This is the equilibrium condition. This is a force equilibrium, and there is also moment equilibrium. You can also get moment equilibrium for the whole laminate. Not that each lamina has 0 stress. It's a laminate has a total average stress of 0. Okay, because there is no external apply load. All the load came from insides. So the inside stress will have a total resultant of 0 according to equilibrium. And those two conditions are reflected by these. This is a force sum to 0, and there's a moment sum to 0 as well. This is a force sum to 0, and there's a moment sum to 0. And those conditions later on boil down to this equation. This turns out to be the equation for the resultant force equals 0, resultant moment equals 0. It looks like, almost look like the same equation, governing equation, when you solve the deformation of laminate under external applied load. Except that this NT-MT matrices are not a true load. They are sort of a hygrothermal load. They're equivalent load, but not true load. But nonetheless, these two NT-MT, these two vectors determine the midplane stretching and curvature here. Okay. And then you can use a midplane. You can solve this equation to get midplane membrane strain and curvature, and those will be the thermally induced expansion and warping of the plate. Okay, since we really have no true external load, the solution of these vectors epsilon and kappa is a thermally induced deformation. You can estimate how a plate would expand in which direction, how much, by solving this equation. Okay. And then the thermal load here is basically calculated as such. Is calculated very similar to your CLT code. You sum over all layers, K equal to 1 to N, delta T minus Q bar multiply your thermal expansion in each lamina thickness, and this is a bending. So you need to program these two into your code to get this vector NT and this vector MT. And then you plug NT MT over here to solve this thermally induced warping and stretching. And then from thermally induced warping and stretching, you get total strain. Total strain is this strain right here. Total strain is this. Okay. And then you subtract out the thermal strain, you will have a mechanical strain. Then you have mechanical strain. Then you use a mechanical strain back into this equation to calculate mechanical stress, thermally induced mechanical stress, and that will be the workflow. Okay. So I'm gonna slowly go through the process how I did on my code. So I'm gonna start with this. I need to calculate NT and MTs, right? These two equations. Now, before I do that, I need to calculate alpha in the XY direction. Alpha in XY direction is like a string transformation. Let me go to my code. This is my code here. This is thermal stress part. All right. So I have these different layers. Each layer is one column like this. That's layer 1. I have layer 2 and 3, and each layer is one this long column. I'm gonna go through one column, then there are repeats. I just copy and paste them, so they're the same. All right. So similarly, I have the layer thickness. This is Z numbers are the top and bottom surface of the layer, the coordinates, Z coordinates. Angle theta is from the layup. I can change layups any number. I can do 45, 45, minus 45, 0, 0, minus 45, 45, like these, like something like that. So you see my angles are copied over from this layup, and the thickness, Z number are allocated automatically. And this is a set of lamina properties I used. All right, so, and then in order to account for thermal stress, you need to input the delta T. Delta T is the difference from a stress-free temperature to your working temperature. Usually stress-free temperature is some hypothetical temperature higher than its service temperature. You know, curing temperature is like an in-between curing temperature and your surface temperature. So I assume that this temperature delta T in this case is minus 75 degree Kelvin. So the stress-free temperature is high than your normal operating temperature by 75 degrees. And the alpha 1, alpha 2 was thermal expansion in the material coordinates, and the alpha 1, 2 is 0. Now, the first thing I did is transfer alphas into the material coordinate system. I use the same string transformation equation I use. It is J37L39, J37L39, which is this equation. So this is exactly how you transform your strains. You use the same, remember you transform a strain from 1, 2 coordinates to XY coordinates. So that basically is the same equation. Use that same equation to transform the thermal expansion from 1, 2 to XY. So this is calculated as strain XY direction. Okay. I made a mistake here. So the layer 1 actually is this. Let me get rid of this. This is misleading. No waters. Where's no water? No waters. No waters. So my layer 1 is this one actually. Okay, so that's my laminate 1. I missed the column here. This is my number 2. So my strain transfer matrix is this one. It's calculated as a multiplication of 3 matrices, the T inverse, and R. Okay. So I basically transform this vector from here to here by the strain transformation. Okay. All right. So that's first step. First step is you construct thermal expansion for each layers, and you figure out where is that? Where is that? Or you figure out alpha x, alpha y, and alpha xy for every layer. That's first step. Okay. That's achieved through applying strain transformation to alpha 1, alpha 2. Okay, vector. Our the second step is doing thermal stress calculation. Is calculate this vector NT. So you see each lamina contributing something to this sum, right? It's the sum of each layer. So I calculated contribution to this vector from each layer separately, and I then sum them up. So if you see the contribution from each layer is nothing but the Q matrix multiply alpha, multiply thickness, multiply delta T, right? Is Q multiply alpha, multiply delta H, thickness, multiply delta T, right? That's the contribution from one layer. And then you have other layers, right? So what I have here, so I calculate the contribution to NT from layer 1 as here. It's the thickness, is the delta T multiply thickness. K17 is the delta T multiply K3 is the thickness, right? K3 is the thickness. Multiply 2 matrix Q bar J47 L49 is my Q bar matrix, and then K22 K24 is my X matrix, my alpha X matrix 22 to 24. Okay. All right. So that's the if I click here, you see all the input here. I have thickness, delta T, alpha, and Q bar matrix. Q bar matrix right here. Okay. So this allow me to calculate the contribution to the NT vector from this lamina. All right. Any questions? All right, then I do this for each lamina. This is contribution to NT from lamina number 2. This contribution to NT from lamina number 3, number 4, so on and so forth. And then finally, I sum them up. This is a sum. See, there's all the add together. See the equation here? It's all of them are added together, all of these contributions from all the layers. And this is my total NT. Any questions? All right, so back to this equation. The other thing to figure out, the next thing to figure out is MT. Is the equivalent thermally induced bending vector. This is the equivalent thermally induced the load vector, load vector, this tension in plane load. This is a bending. Now to calculate that, you need to basically again calculate the contribution from each lamina. And each lamina has a contribution which is equal to the Q bar matrix multiplied alpha, multiply this H square minus H square term, multiply half of delta T. And then you run through this from lamina 1 to n. So what I calculated MT for each lamina here. I have all these contributions, and then similarly I sum them up over here. Okay, I calculated over here. I sum them up over here. Okay, I just use a similar set of equations. So my 1/2 H square minus H square is pre-calculated over here, and that gets multiplied in. Let's look at the terms here. So I have this term. This term is this term. Is 1/2 H squared minus H squared. That's captured in the single number here. I pre-calculated it. And then I have this matrix J47, L49. That's my Q bar matrix. And then I have this vector K22, K24. That's my alpha in XY coordinates. Okay. So you multiply all them together is a contribution from single lamina according to this equation. Right? All right, so similarly to the way I treated NT, I sum all of them together over here. You can look at my equation here. It's everything summed together. Layer 1, layer 2, layer 3. They each have a contribution to MT, so I sum them up. Okay. And then this vector is my total thermal load. All right, so once I have this vector, I'm ready to solve this equation now. I'm ready to solve this equation. I have my NT-MT. So the ABD matrix are built the same way. They're no different than before. So you already have that. Okay. So what I did, I basically, this is normally is where I put mechanical loading. I just copied all the thermal loading into that place. So this end up solving this thermally induced. See, I copied this into here. So and then my calculator will automatically solve this equation by multiplying that thing with the inverse matrix. This is the inverse ABD. I multiply inverse ABD with this vector here, and I get these this vector here. This vector is epsilon 0 and kappa. That's the thermally induced in-plane stretching and curvature terms. Okay. Any questions so far? Am I going too fast? All right. So far, so good. Okay. So what happened after you solve this epsilon 0 and kappa? You can use the solved epsilon 0 kappas to calculate total strain. The total strain is still dependent on this, and you can calculate this using the Kirchhoff assumption that we learned before. The Kirchhoff assumption depends on membrane stretch and bending, and then you can depend on the Z number, you can calculate strain everywhere, right? That's a Kirchhoff assumption. So I calculate total strain, which is here. This is the total strain using Kirchhoff assumption. I calculate for each lamina, I calculate the top layer and bottom layer. Top layer, bottom layer. Total strain. Then I calculate thermal strain. Thermal strain is basically strain transformation result. Is alpha x, alpha y, basically. Thermal strain. And then I subtract thermal strain out of the total strain. I got a mechanical strain. But this is thermal strain. See, you see, this is the same as this. Oh, there's angle here, so it's not same. It's 45. So the thermal strain is basically the free expansion strain. Assuming if you free up each lamina, let it freely expand from the temperature gradient, you will get a thermal strain. So which is this term here? This ET term, epsilon T term. So the mechanical strain is the total strain subtract the thermal strain. So I have that here. I have a mechanical strain here, which is K62 minus K52, which essentially is my total strain, 62 minus K52, which is the thermal strain. Okay. So this subtraction is captured over here. This equation is essentially captured over here. All right, so next step is I use a mechanical strain to calculate mechanical stress, basically using this equation. You have mechanical strain, you multiply Q bar, you get mechanical stress, okay? Which is here. My mechanical stress, this term, is my Q bar matrix, J47, L49 Q bar multiplied K57, K59, which is mechanical strain, this one, right? Then I get my stress, thermally induced stress, then I can transform that stress into 1-2 coordinates. I guess thermal stress in 1-2 coordinates. So and then these are the real stress. These are misfit stretch due to the thermal differential thermal expansions. And you can do other estimation based on whatever you need to do. You can see if the thermal stress induced failure, things like that, with matrix crack, and you apply failure criteria, things like that, to on the stress calculated in the 1-2 coordinates. And if you have a combined thermal and mechanical load, you would put a combined loading over here. You would calculate another problem with pure mechanical loading. You calculate stress, and then you superimpose them together. So your true stress with both thermal load and mechanical load is the combination of your solution with a pure thermal load and pure mechanical load. You put them all together. You sum them up. Okay. All right. Any questions so far? All right, so let's look at this example here. So I'm gonna use my code to solve this example. So I'll share this with you later on today. I'll upload this part. So you should, once you program your load, you can also try this problem. This problem is from this book. You can also look through the book. This part from this book here. I need this. Just actually just one. So this problem is calculate the residual stress at bottom surface with 90-degree ply in a 2-ply 090 graphite epoxy laminate subjected to a temperature change of minus 75 C. So it's a thermal stress problem. Use the unidirectional property of graphite epoxy laminate from table 2.1, each laminate 5 mm 6. This is a table here. So we're going to use the property here. This is the property you want to use, graphite epoxy. See, I have an issue with using this code, using my code solves. My code, I hard program 6 plies. This is 2 plies. So I can actually tweak my code to solve this. I just assume I just slip the 0 degree into 3 plies. Now each ply is 5 mm thick. I can divide 5 by 3. I can figure out equivalent. So basically, I cut each of the 0 and each of 90s into 3 sublayers. That way, I don't need to change my program. So I just calculated as an equivalent 6 ply. I reduce the thickness of my ply to match the thickness here. So I should have same results. So that's the trick I played. So I show you here. I'm having the input material property, which is this property here. This set of property came directly from this table. I just put a E1 here, E2, gamma 1, 2, G1, 2 into this. I also use alphas, alpha 1, alpha 2, things like that. These 2 number also goes into my code, which is right here. This is my alphas, alpha 1, alpha 2, and this is my E1, E2, U1, 2, and U2 1 is calculated, G1, 2 is from the table. And delta T is a minus 75 degrees C according to the problem. The problem says minus 25 degrees C. Minus 75 degrees C. I had minus 75 degrees C. Okay. So I'm gonna have 3 zeros and 3 90s, right, to match the problem layup. My thickness is not a 1 millimeter, it's 1.6 millimeter. So if you add this 3 together, it's 5. That matches thickness of that problem. Okay. These 3 add up to 5 as well. So that's my layup. See in my layup, I automatically get copied over here. I have a 0, 0, 0, and 90, 90, and another 90. Okay. All right. So, and then my program automatically updates. It'll give you the NTs for this layer, NT for this layer, for this problem. I guess alpha 1, 2 is 0.2, 0.225, 10 to the minus 10 to the minus 4, and that will be these 2 numbers right here, alpha 1, alpha 2. And then after transformation, you got alpha x, alpha y, which is these 2 number. After transformation, x, y is these 2 number. 0.225, 0.2, which is over here, 0.225, 0.2, these 2 numbers right here. And this is for the 90-degree plies. Not for the 0 degree is this 2. 90-degree plies, this 2 number reversed. 0.225 is alpha x, 0.2 is alpha y. For 0 degree, 0.2, 0.225. For the 90 degree, the other way. So for my 0 degree is 0.2, 10 to the minus 7, 0.225, 10 to the minus 4, which is these 2. And for 90 degree is over here. These are 90s. See, these 2 numbers are reversed. You see 0.225 and 0.225, 0.2, 0.3 reversed. So they match exactly to this equation right here. All right, then I calculate Q bar 0, Q bar 90 is which my Q bar here, the Q bar. This Q bar 0. Let me minimize this so you can see both. This Q bar 0, it matches exactly this. This E to 11 is over gigapascal 10 to the 9. So 181 10 to the 9 is 1.8 10 to the 11. which is what I have here, 1.8 10 to the 11, right? 2.89 10 to the 9, which is this 2.89 10 to the 9, and 1.05 10 to the 5, and then 7.17 here. So that's my Q bar. Q bar 90 also match. And then thermal load. Thermal load is calculated as such. You add all these layers together. You sum them up, right? In this case, they have 2 layers, but their thickness is bigger. I have a 6 layer. I have smaller thickness. It's the same ply, so it doesn't matter. You should sum to the same results. So if you look at my sum is over here. Thermal load is right over here. These are my thermal load ends. All right. It's exactly match this. It's a 1.13 10 to the 5. All right. This is the bending. Bending is this one. Once you sum that up, it's 1.53 10 to the 2 right here. All right. So once you got NTs, MTs, the next thing to do is to copy NT, MT over here and solve the governing equation, which is this inverse ABD multiply this n vectors, and I have this. This is the solution of my use black. Use this is my solution. All right. This is my mid-plane curvature. This is a membrane strain at the mid-plane, and this is a curvature. You can see it warps quite a lot. It actually warp into a saddle shape. You see a warp up in X, warp down in Y. You can also see there's a shrinking in XY directions. It is shrinking because you're cooling down from higher temperature to lower temperature, negative temperature change, right? All right, so that's the solution of epsilon 0 and the kappas, and then use this epsilon kappa, you can calculate the total strain, which I've calculated over here, total strain, right here. This is calculated using the Kirchhoff assumption from these numbers. Using Kirchhoff assumption, I can calculate total strains right over here. Oh, not over there. This one. Actually here, this is the total strain. All right, so here's the solution for the epsilon X, epsilon Y, and then here's my solution right here. You see, these are exactly this 3.9 10 to the 1, 2, 3, 4, 10 to minus 4, minus right here, same number, 0 here. This is a minus 1 to 7, 10 to the minus 1, right? Plus and 0. So this matches this exactly. This is the epsilons and kappas. All right. And the next thing you do is you calculate the thermal stress. So I calculate the total strain. I subtracted this is the key part of it. Back to the slides. What we have is we have gone so far as to figure out total strain. But we want to figure out what the mechanical strain is so that we can calculate mechanical stress. So mechanical stress only depends on mechanical strain. So I need to subtract the thermal strain out of the total strain. I need to do subtraction to get mechanical strain. Then I can plug mechanical strain into this equation to calculate mechanical stress, right? So that's accomplished in my code like this. So I figure out the free thermal expansion strain for each lamina, which is this matrix. This is at the top, the other is bottom. They're the same, right? Then I subtract. This is the difference between thermal and mechanical. This is my thermal and total. This is my mechanical strain. I say strains underscore mechanical. That's my mechanical strain. It's a subtraction of this of the thermal effect out of the total strain. The total strain is calculated using this set of numbers, okay, and a Kirchhoff assumption, okay. And then what I do is I calculate stress now because I have mechanical strain, so I can calculate mechanical stress. Mechanical stress here is calculated with mechanical strain, okay. Then I transfer that mechanical stress into 1-2 coordinates. I calculate all the stress in all layers, okay. Let's compare these results. So I have this is the total strain at the bottom of the zero. It's -1029, 2.45. So my total strain at the bottom zero is towards here. Here, right? This is my strain at the bottom, which is, and you can see it is exactly this, -1.029, 10 to the -3, 2.476, 10 to the -4, and 0. This is essential 0. 2.2 is -19. Right? This is this set of vector right here. So my code produced exactly the same results as a number in that book. It's basically matching exactly. And my thermal strain, I can figure out my thermal strain, which is here, 0.225. Where's my thermal strain? Thermal strain is, I need to shrink down a little bit. So my thermal strain is here, right there, right above it. This is my thermal strain, 0.168. This is my thermal strain for that layer, which is exactly this number. I subtract it, then I subtract this out of, I subtract thermal strain out of the total strain. Then I got a mechanical strain. Mechanical strain is this 0.68, which is this right here. This is the mechanical strain. Right over here. So compare notes. My mechanical strain is this. This is for the 90-degree layer, which is exactly this number right here, 0.68, 6585, 0.249, and this is essentially 0, minus 4.5 10 to the minus 101. All right, then I can multiply Q bar matrix with a mechanical strain to get my stress, right? Which is over here, stress, XY. You can see it's calculated by matrix multiply Q bar with mechanical strain, K59, right over here, okay? Okay, so. And then I can compare the mechanical stress, which is this number. This is 90-degree at the bottom, which is this number. In my case, I calculated. I need to look at the bottom of the 6th layer. All right, so that's my mechanical stress. Right over here at the bottom. All right. Let's move that to the middle. Compare these. Right here. These number and these number. 47. All right, so it's exact matching. 7.5 E6, 4.7 E9, which is this 4.718 is I have a 4.719. It's almost the same. And these will be the thermally induced stress in that layer. Okay. Yeah, I compared other things. They are pretty much all match. So this code matches the set of calculation in that book almost right on. There's no, I don't see any differences. Pretty much right on. So what I encourage you to do is you update your code, and then you compare. I upload this set of slides. You compare your calculations step by step with this set of data, from this point to this point to this point, all the way down to here. If your code check out with this set example, very likely you have a correct code. Okay. So this is basically a sanity check for you. I check my code against this. So basically, you know, match exactly. And I want you to do this before you embark on the final project to basically nail out all the bugs that potentially you potentially make, and then match this. All right, I want you to work on this, and hopefully by the end of next week, you'll have everybody's done with this. Okay, then we'll lay out and work on the final project. Does that sound like a plan? Is it reasonable? Can you all get this done by the end of next week? All right. Thomas is pretty confident, I guess. Any other questions and comments? All right, if you don't have any comments, I'm gonna close down here. I'll upload the recording, and I'll upload this set of slides. I named it as example thermal stress calculation. Example of thermal stress calculation. You can just download it and work on it. Okay. All right. I'm done today. Any questions? No question. I'm gonna close down here. Okay, I guess there are no questions. All right, you all have a good weekend. I'll see you guys on Monday. All right, bye-bye.